So I will pick up on a response to the question that was just asked. I'm going to start here. Obviously, you can tell, those of you who don't know me, that I don't belong in the west of the USA, at least I'm not a native of that part of the world. So the question for me always is, where's the west? If you look at this Google image of, which I'm sure we're all familiar with, of the USA, the lower 48, it kind of goes from green to brown as you move from right to left. And I assume with climate change, the brown bit's probably going to move eastwards, and the green bit might get greener if it's really going to suffer more rainfall. But I want to pick up in thinking about where's the west with the importance of story, picking up on what Mike said at lunchtime. And I'm going to bet that maybe none of you have heard of Sonora Bab. Say, anyone online want to put a comment in the chat if you've heard of Sonora Bab? Who was Sonora Bab? She was an American journalist, poet, ecofeminist, novelist. She was born in Oklahoma in 1907, the year that it became a state. After moving around, following after her itinerant father, who was a gambler, the family lived in Kansas, Oklahoma, eastern Colorado for a while, where they lived with their grandfather, trying to make a living growing sorghum, broom corn. And eventually she made her way to LA in the 30s, worked as a journalist, and for a few years she worked for the FSA, the Farm Securities Agency, which was desperately trying to deal with the influx of workers from the Dust Bowl into California. She was an anthropologist, self-taught by that time, kept notebooks of her work in the camps, and her boss, Tom Collins, gave copies of her notebooks to John Steinbeck. And she had written her own novel about the Dust Bowl by that time, which wasn't published until 1994 because her publisher said that the world couldn't stand to read two Dust Bowl novels back to back. But actually, a lot of her work underlies what Steinbeck produced. People think it's not 100% known, but the difference between her novel, whose names are unknown, and Grapes of Wrath is that she had lived through the experience of being in the Dust Bowl. She had moved west as a consequence, and so whose names are unknown actually documents the experience of being in the Midwest when the Dust Bowl struck. I'm just saying all of this to point out that we know what climate migration looks like already. It happened here. And we're still living with the consequences of that because, of course, the first Farm Bill was written in 1933 as a response to some of what was happening then. And if you don't think that we're living with the consequences of when the Farm Bill was written and why it was written, then just think about how much funding there is for research versus some other things in that bill and the huge historical momentum that's behind that bill and what it pays for. So it's important to understand story and to use story in what we're thinking about. I'll put my hand up and say it was me that said people aren't going to want a big list, Jim. I was wrong. His big list was really interesting. I'm not a climatologist, so I'm kind of working on, this is a sort of assumption of what the West, wherever that is going to look like midway through the century. I don't think anyone would argue with any of that. I will say that also whether you're in the West, if you're working in the sort of university/federal government system, depends on which program you're working for. If you're in NPDN, then Colorado is not in the West, it's on the Great Plains. If you work for the IPMA groups, then Colorado is in the West because they've got one fewer region than we do. If you work for the state in plant regulatory world, the National Plant Board, where the West starts varies also from where NPDN thinks it started. And that's not a trivial point either, because when you're trying to organize things and coordinate, labels matter if they refer to particular things. But what are we seeing more of in the West? And I'll say that this is a heavily California-centric view, but we're seeing more Phytophthora, which people might find surprising, given that their kind of informal name often is the water molds. But there is the sudden oak death epidemic, which is raging up the West Coast. May or may not be, I'm going to make similar comments to Jim here, it may or may not be attributable in part to climate change. It probably isn't moving as far inland as it might have done, because the humidity near the coast certainly helps the pathogen responsible spread. But we've seen in NPDN, we've seen the arrival of a completely new Phytophthora species that's showing similar indications of being a problem for the nursery industry in just in the last 12 months too. Water extension plant pathologists on the West Coast worrying about. We're seeing a lot more issues with fusarium species. So these are soil-borne fungal pathogens, which there are some new disease complexes involving endemic fusarium species, but they seem to be behaving in a different way these days than they have before. And the processing tomato industry and the lettuce industry are having big issues with those in California, Arizona. We're having renewed problems with Sclerotium ralsii. It has a new name now. People who do fungal taxonomy like to rename everything every so often just to bug the rest of us. Informally, that's another soil-borne pathogen called southern blight. It's a high temperature pathogen, and as our soils warm up, we're seeing more issues with that pathogen in crops like potatoes. I'm going to give a shout out to Len Coop. I don't know if Len's still on the call or not, but picking up on Brittany's talk this morning, way back, almost as soon as I arrived in Davis over a decade ago, one of the first things we did was work with Len through something called the Western Weather Work Group to make a phenology model for Western flower thrips, which is an extremely prevalent pest species in its own right in many crops because of cosmetic damage, but it's also a vector of what are called tospoviruses. They're RNA viruses. Unusual in plant viruses, they can also multiply in the vector. So they're propagative in the vector. We're seeing renewed issues with two different tospoviruses, in particular in the West, TSWD, tomato spotted wilt virus, partly as a consequence of having a virus that can multiply in its vector as well as in the crop. When you get more generations of the vector, you just get more virus because it's multiplying in the vector too. But the lettuce industry in the Salinas Valley, where 90% of your iceberg lettuce comes from, is having a major issue at the moment with impatiens necrotic spot virus, INSV, and other tospovirus. So same vector, different virus. And one of the main reasons why INSV has exploded in the Salinas Valley is that the winter temperatures are now routinely above the base temperature for thrips development. But to track some of these things, we're using a phenology model that Len and I made from published results that were available in the literature from temperature experiments. And those insect temperature growth experiments, if you just want a simple phenology model, do translate pretty well to the field sometimes. So a thrips model that we made a decade ago is regularly used by both the processing tomato and lettuce industries to kind of track thrips phenology, and that helps a little bit with the decision making. Jim, I'm going to see your leafhopper and raise you my leafhopper. I'm going to put Circulifer tenalis up against your guy. Again, the beet leafhopper, it's a desert adapted insect. It's been in the United States probably since Europeans arrived and brought it with them with their sugar beet. It regularly causes problems for the processing tomato industry, again on the West Coast, because it transmits a cartovirus, beet curly top virus, which is single-stranded DNA virus. Somewhat similar to your story, Jim, 2 years ago, we had extremely unusual wind and temperature patterns in California at a time of year we wouldn't normally expect to see them. Extremely strong winds from the south to the north, and a few months later, curly top virus showed up in northern counties in the Central Valley where it would not normally be a disease. And unusually, genotyping of the virus showed it was a strain of virus that hadn't been seen for over 80 years that was first detected in spinach. Where that reservoir virus had been, why it hadn't shown up in any of the places where it would normally have shown up, we don't know. But it popped up because of an unusual weather pattern and it disappeared again. And as weather patterns change, we're seeing all kinds of unusual problems. So just to give another example, with the citrus industry in the Central Coast, a normal time of year to apply an insecticide treatment to keep things like the Asian citrus psyllid under control would be December. In the last couple of years, the growers have had no available spray days in December. A lot of the applications are done by helicopter in that area because of the terrain. There were no available days in December for application because the Santa Ana winds off the desert started blowing earlier than they would be, and the wind speeds were too high constantly that month for any applications to be made. So completely unexpected effect. So far, we're not seeing that it's led to any major issues with disease outbreaks, but nobody saw that coming. And it might mean if that's going to be the weather pattern from now on, that growers are going to have to rethink their management plans. Another big problem related to vector populations, we're seeing the glassy winged sharpshooter, which is an invasive insect from the southeastern region of the USA, is expanding its range. It's moving northwards as we get more degree days. Why is that a problem? Because it's a vector for Xylella fastidiosa, which is the cause of Pierce's disease in grape. That's the same pathogen that has different strains, but the same species that has caused huge issues in the Mediterranean basin through the destruction of olive. So we're seeing this pattern a lot particularly with vector diseases, as the vectors are having more generations, as their phenology is changing, and in some cases, as they allow the viruses to multiply more, we're seeing vector diseases in particular become more intense problems. Some good news. In the decade that I've been in Davis, we kind of pretty much concluded that something we thought was going to be a major issue, pitch canker of Monterey pine, turns out probably isn't going to be a big problem because we have less coastal fog than we previously did. And so that fungal pathogen is not making inroads into the Monterey pine in the way that we thought it would. The central coast of California is the last kind of natural habitat for the Monterey pine. It's not a massively widely distributed species in terms of natural habitat, but Pinus radiata, the Monterey pine, is a hugely important commercial pine species in the rest of the world. But so Fusarium circinatum seems to have lost out as we've lost our coastal fog. Some new things that are in the balance. This is somewhat like a DDRP approach for the Asian citrus psyllid that we've been working on in California. So ACP, the Asian citrus psyllid, is the vector of citrus greening. Is citrus greening important? It certainly is if you're in Florida. Florida's lost about 70% of its citrus industry over the last 15 years, partly as a result of hurricane activity, but mostly as a consequence of the arrival of citrus greening. It looks as though, thankfully, California is not going to go the same way. We didn't know that when the pathogen system first turned up in California, but why is it not going to go the same way? Because it's too cold in the winter and too hot in the summer. So we're in the balance. If the climate changes, if we get warmer winters, we'll lose some of the winter kill that's keeping the psyllids in check at the moment, but we'll gain summer kill as the summers heat up. So we can't tell with this one where we're going to go in the future, but a kind of combined temperature phenology approach. So I want to speak to you later, Brittany, okay. is letting us at least give the industry some advice. That's good news for them because the annual cost of the HLB containment program in California is about $40 million a year, of which the industry is paying 50% itself directly from assessing itself. So that's putting a few cents on the price of your oranges every year. So they'd like to do less, and we're kind of in this dangerous situation where we want to recommend that they can do less, but it's a big deal to say, yeah, you can afford to control this devastating disease less. The climate and the terrain are going to help you out. Okay, so I want to now jump to some social science, or at least some human behavior. So I got frustrated after about 20 years of trying to be an epidemiologist, that I would do what people expected, which was make predictive models and give them to growers to say, if you want to cut back on your pesticide use but not maximize your risk, adopt this model. And they would go, yeah, very interesting, Neil, no thanks. And so I decided that in order to get more impact, I needed to understand how people were making decisions. So we've worked for a long time on trying to apply information theory to that problem. And to cut a long story short, giving people more information doesn't necessarily reduce their uncertainty. And the reason why that happens is that if you express things in terms of probabilities, lurking in the background, there's this thing called information entropy, which was first kind of, the inventors discover things or invent them, I don't know. But Claude Shannon discovered the relationship between uncertainty and probability during his work for the Bell Labs in the 40s. And essentially, if you look at the graph, the horizontal axis is showing you the probability that something might happen, going from 0 to 1. And the vertical axis is showing you how much uncertainty there is as you move along that scale from 0 to 1. So you can imagine at the top of the curve, if at a probability of 0.5, there's maximum uncertainty. You're in coin flip territory. As you move either towards 0 or 1, the amount of uncertainty goes down. So now imagine two growers. They're indicated by the two solid symbols. We give them both the same information about the likelihood that disease is going to happen, but the grower who starts towards the lower end of the scale, who's more optimistic to begin with that the disease isn't going to happen, actually experiences an increase in uncertainty if you tell that grower the disease is going to happen. On the other hand, if you're already past the 50-50 point, indicated by the solid diamond on the right-hand side of the curve, if you tell a grower whose prior is that the disease is going to happen, and that grower is already pretty certain it's going to happen, you just confirm what they already think, and their uncertainty goes down a little bit. Same information, same circumstances, but the perceived uncertainty depends on where they start. So I'm going to turn to an unlikely source for help here, the late Defense Secretary in the Bush administration. And he famously said at a briefing in 2002, these things about risk and unknowns. And some clever person at slate.com turned it into this beautiful piece of poetry. Okay, the unknown. And this is actually directly what Donald Rumsfeld said. As we know, there are known knowns, there are things we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns, the ones we don't know. He missed something. For completeness, he missed the known unknowns. Things that you know, but you don't know that you know them. Okay. And those are important. Okay, so to kind of complete the square here, and social scientists love reducing everything to a 2x2 box if we can. In this case, we can. So at the top, we've got risks, and Marty, you've got risks written on one of your sheets. So this is relevant for this. Okay, so there are knowns and there are unknowns. Okay, and that's for sure. And then we've got on the left-hand side, we've got what's called the epistemic state, which is what your level of knowledge is. Okay, to give it its fancy term, your epistemic state. So you either know something or you don't know it. Okay, that's your epistemic state, if we make it binary. So that classifies everything. So there, Donald looking pensive in the middle there. So if we go in the top corner, he knows that he knows some things, and we can see that those are quantified, or we could quantify them. And then when it comes to, if we go across to the right, there are things we know we don't know. So those are known unknowns. And we can call them gaps. And then if we come down to the bottom right-hand corner, which he mentioned, there are things we don't know that we don't know, which is our zone of total ignorance. And then the one he missed is the bottom left-hand corner, which is things that are known, but we don't know that we know them. So we lack insight into our own state of knowledge there. Okay, So we can take that same idea and create this thing, which I somewhat jokingly called Rumsfeld space, to classify our problems. And I think the issue we have with climate change is that a lot of what we need to do falls into the UU corner of Rumsfeld space. So it's the unknown unknowns. And where we feel comfortable, so where we're not at the top of the entropy curve, is in the KK square, which is the known knowns. Okay. So quite often to solve problems, we have to move out of the known known square. And the question is, how do we do that? And I'm going to turn to a little bit of model selection theory, and this helps explain why humans do lazy, bad things instead of good, complicated things. If any of you who are involved in statistical work will recognize this idea of model selection, the Akaike information criterion, which basically says if you want to make predictions, your model really needs to balance two things, which are accuracy and complexity. And it gives a formula based in information theory for how we can do that. If you look at the lower version of the model, it really says that there's a constant, which is a sort of scalar, which is the number of data points you've got, the big N. And then there are two things, which is the log likelihood, which is a measure of the accuracy of the model. And I'll say in passing that there are experiments done with macaque monkeys where they can stick electrodes into their brains, the poor little things. Obviously, we can't do that with humans, but we know enough about human cognition now to know that, sorry, I should say monkey cognition, that brains learn by changing log likelihoods. So what we do in statistical model fitting is replicated in mammalian brains. It's how we gather information. So something like this probably happens in your brain if you want to make accurate predictions. You've got some background data, you've got how good your model is, and then K, the little k here, is the number of things, the number of adjustable parameters that you have to learn to get your model to be more accurate. Okay, so this presents a kind of balance equation. We're looking to kind of trade off accuracy against complexity, and you can see where complexity enters. So if we take this idea, we can rearrange this little equation. Suppose we have a way of doing something, and somebody like me says, don't do it that way. I've got this better model. It's more accurate, but you're going to have to learn some stuff in order to use it. Here it is. Well, now we can use this to say whether it's likely that somebody's going to take on that challenge or not by rearranging the model. So a little bit of arithmetic, a little bit of algebra, and now we can say if my new model is L2 and the old model is L1, if my new model has n new parameters that the old one didn't have, it needs to be e to the n times more accurate than the old one for the trade-off between complexity and accuracy to be worthwhile. Okay, so it gets exponentially less likely that someone will adopt it every time you add one more parameter, one more thing for them to juggle. Okay, so now if we think about the kind of situation we're facing, last slide, we're asking people constantly to, when we're thinking about dealing with things like climate change, to move around in Rumsfeld space. And if we add more complexity, what does that look like? So let's say we're comfortably in our KK square. We know what's going on. We've got everything quantified. And in order to do that, we've got four things that we have to juggle. Okay. Let's suppose we're going to say there are two new things that we can add, or we can afford to add two bits of complication to the way that we're going to do this. We're going to gain some accuracy by doing that. If we want to move in by filling gaps in our knowledge, so that's moving to the right, then what does that look like? We add two new things, two different colored circles here. What would it mean to say that we add two new things by adding two unknown knowns? So two things that we know, but we don't know that we know them. Well, we could say that might be identifying two overlooked interactions between among the four existing things. What's the big problem we face in all of this stuff that we're trying to do? We're moving in a black hole in the UU region of Rumsfeld space. We don't know. We don't know how many additional parameters we need to juggle a lot of the time in order to get good predictions about what's going to happen. And I think part of that problem comes back to what Jim said, which is that the underlying interactive complexity in what we're doing is simply so large that it's impossible to say at this stage how many additional things we're going to have to juggle to get any level of accuracy that we want to work with. I don't have an answer for what we do about entering a black hole, except dive in and find out what happens. I'm done.
Henceforth to be known as the stack McRoberts calculus.
I think what happens when you enter into the black hole is you're gone. That's physics, never mind.
I'm just feeling that for that macaque monkey right now. Questions for me?
Could you review how you know that E to the N is accurate? Is that based on the macaque monkeys?
No, that comes from model selection theory.
Okay.
So the AIC, the Aki-Iki information criterion, is a commonly used metric for us. If you want to choose a model from a competing set of models, you can set the accuracy at a known level, and then once the accuracy that you need is set, the trade-off equation will tend to pick the simplest model that achieves that level of accuracy. By rearranging that equation, you can pull out that factor that says, if you have the same level of accuracy for two models, what's the relation? How much more accurate does one need to be than the other to justify the number of additional parameters that you include? It's just kind of a way of thinking about the trade-off between complexity and outcome.
Yeah, it's brilliant. I was just curious what the background was.